Okay, 7:30. Let's get started tonight. So we were done with this sequential circuits and storage elements, flip-flop concept, and all this stuff. So these 2 days, we will be reviewing mostly the CS47 study that we did, at least in my class, for the adder, subtractor, multiplication, division circuits. So these are kind of, for my former students, this is more like a review. For new students, probably it's going to be a new topics for you. So please pay attention to those topics who are at least new to this part of the discussion. So this is mostly covering the adder, subtractor, multiplier, divider, all integer operations, how they're done, and what the logic circuitry behind it. We'll be doing that. And after that, we'll do a little bit study on a potential ALU design. We'll show one of the design that can be done to make a real ALU from the logic gate with using the logic gates and logic sites. So that's our target for this module. So this is module 4, and then module 5 is the where the real fun begins. Okay, module 5 is basically I mark it as a start of the real computer architecture study. So far till module 4, it is mostly review of CS47 computer organization study. And then from the module 5 onwards, it's a real hardcore architecture study for you guys. So you need to pay double attention to those topics. Those are brand new topics for you. Saying that, any question from anyone, like and on any topic, class related topics? Okay. So let's start with a problem tonight. So I have, if you look, go to my Jamboard and look at this thing here. I have given a little diagram which basically described an XOR implementation with a minimum number of NAND gate. Like usually we think like, okay, if we derive straightforward, we'll need like 5 NAND gate to implement that. But there is like a little bit more optimized version available, which uses the 4 NAND gate to implement an XOR gate. Let me first describe how this can be derived. Okay, how this can be derived. So give me a moment. Let me turn on my. Okay. So problem in hand is A XOR B. Now note, there is a little note. I use XOR as this. Okay, this is a Verilog notation, I believe. And sometimes I also use this. This is also a standard notation for the XOR. This notation is not available on the standard keyboard, so we don't use it in any programmatic language. Programmatic language where Verilog uses this notation. So any notation like this or this is practically tell you the XOR. With that point, I just remember one point for you to like clear that from your Math 42 study, you probably came across sign like this, which is very similar to this one. This is practically your A and B. And there is one more like this one. This is basically A or B for us. So we never use that math symbol, okay, in this class. We always use our digital logic symbol, like an dot or plus or caret. So don't mix up with your Math 42 symbol in this case, all right? Okay, so our problem in hand is how can we derive this compact notation for circuit for the XOR. So we all know XOR by functionality is AB bar or A bar B, right? So this one by De Morgan, we can write AB bar whole bar NAND A bar B whole bar whole bar. This is by De Morgan. And from there, let's say, from there, what I can write, this term as 0 or AB bar whole bar. Next term 0 or A bar B whole bar whole bar. Now this 0, let's play with the zeros. I can write it as AA bar, right? And this becomes like AA bar, AB bar whole bar. And the other 0, let's write it like a BB bar, and A bar B whole bar whole bar. From there, what we can do is basically make it like this: A bar, B bar whole bar, and then B bar or A bar whole bar whole bar. Now from there, what I can write is just hold on. From here, what we can go there, how we can go here. Let's hold on. From here, oh, De Morgan, use the De Morgan on this. So this is like writing A bar or A bar, B bar, whole bar, and B bar or A bar, B bar, whole bar, right? We used a De Morgan over here too. That gives you this whole bar. Now, from here, what we can say, this part is basically A bar or A B by De Morgan. We apply De Morgan over here, or B bar or A B. This is the same term, right? So use the De Morgan over here. And yeah, I think we don't need this plus anymore. Okay. And there, it basically now we can say this is like an A B whole bar, B A B whole bar, whole bar, whole bar. Like this is again by De Morgan. So we apply De Morgan conversion from on top of these two terms, which gives me AB whole bar, right? This one. So that's what it is. Like this one is A, and this one is B, and this one is your AB whole bar. This is your AB whole bar, right? So let's note it down. AB whole bar, and NANDed now with A. And similarly here it is like B NANDed with AB bar whole bar, and then this whole thing get NANDed together at this point. So this is how this minimum construction of XOR gates come into place. Question? Okay. If we don't have a question, then 742. Okay. Let's think of a problem like this. You have a 32-bit adder subtractor. Circuit with all NAND. And circuit here we are basically talking about the ripple carry addition type circuit that we studied in this lecture, ripple carry addition. But we need to work on the adder subtractor combined module, that one. Question is how many transistor, we all know that NAND configuration, right? Transistors are needed to make it. So that's the problem, okay? So let's take about 5 minutes to think yourself, okay? So 750s, and then I will open up breakout room for you for 10 minutes to discuss among your peers in your study group. So that, and after that we'll discuss the solution, okay? So 5 minutes from now, think yourself, and then I'll open up the breakout room for you. Okay, let me open up the breakout room for you guys. Why it is not assigned? Ah, what happened? Breakout room, create, reassigned. Okay, okay. Okay, I'm opening room for all now. Okay, I think breakout time is over. Let's wait a few seconds, all of them to come back to this session. Yeah, I think all of you are returned. So any group or anyone wants to volunteer about the answer? How many transistors?
I guess I could share what we got.
Sure.
Okay. So to figure out how many
Did you
transistors
share
are,
any document or something?
we did it in the chat.
Okay, sure.
Um, so first of all, we need to figure out how many transistors we need for one bit. Then we can multiply that number by 32, and we'll get how many transistors we need for the entire thing.
Mm-hmm.
So yeah, here's the math I did. So an inverter is 2 transistors. So for 1 bit, we need an inverter, a multiplexer, and a full adder. So an inverter is 2 transistors. A multiplexer is 1 NOT gate, 2 AND gates, and an OR gate. Each AND gate 6 transistors. Each OR gate's also 6 transistors. And the NOT gate's 2 transistors. So put that all together. Each multiplexer is 20 transistors. And then for the full adder, we first need to do a half adder. A half adder is an XOR gate, which you've shown, and an AND gate.
Mm-hmm.
So eight XOR gates, 4 NANDs, each NAND's 4 transistors. So that XOR gate's 16 transistors, and the AND gate is going to be 6 transistors. It's an AND gate in the inverter, so that's 6 transistors total. So 2 half adders is 44 transistors, and then you have an OR gate for the carry bit. So that's 6 transistors. So each full adder is 50 transistors. You put that all together, you get 72 transistors for 1 bit, multiply that by 32, and I got 2,304 for the 32-bit adder subtractor.
Okay, okay.
Um,
First of all, where did you use the multiplexer?
For the subtractor adder, you need a multiplexer to switch between adding and subtracting.
Okay, why didn't you go with the XOR gate there?
Oh.
Yeah, I think that would minimize the comment. This is okay too. This approach is okay too. I
Oh.
think one thing you guys missed is that I asked for making it with all NAND gate. So, or you need to translate into the NAND as well.
Oh, okay.
That's the XOR.
Oh, I did miss.
That the AND. So I think that's the part I think you missed. But otherwise, that counting looks okay.
Okay, yeah, I think the approach is good. I just missed some of the
Yes,
instructions.
yes, yes.
Yeah, I'm
So
sorry.
for others, like let me try to do it. Okay, let me try to do it. Guys, just go and match it. Okay. So let's say here is my approach. Like I tend to think about transistor late in the process. So I start with an half adder. Like that is the most like lowest most building block for me at least, right? And that contains, as we say, one XOR plus one AND, which
Yeah.
practically means 4 NAND plus 2 NAND, which is like 6 NANDs. Now I go and move to the 1-bit full adder, which is 2 half adder plus 1 OR, right? And 2 half adder, we already computed that, is 6 NAND. So 2 multiplied by 6 NANDs plus 1 OR is practically 3 NANDs. So A or B equals A bar, B bar, whole bar. So each of them are NAND and whole thing is a NAND. So 3 NANDs. So this gives me about 15 nands for 1 bit full adder. So 1 bit half adder to 1 bit full adder. Now I construct the 32-bit ripple carry adder, that the core part of it, which is 32 multiplied by 15 from here nands, which is about like 480 nands. And then we need to add the XOR. Remember this circuit, like we have operand A and B, and then let's say if it's a 4-bit or something like that, it has a XOR gate. One is with the bit and other part is that mode SNA. So each bit calls for one XOR. So that means to make it an like add subtraction circuit, we need to add like this 32 XOR, which is 32 multiplied by 4 NAND equals it's 128 NANDs. So that means total is 128 plus 480 NANDs equals, it's basically comes down to 608. Is it 608? Yeah, NANDs. And now I think about the NAND. Okay, each NAND has 2 PMOS, 2 NMOS, so total 4. This implies it has total 608 multiplied by 4 MOS transistor, which is about 2432 MOS. Like each of them is like NMOS and PMOS. Each type counts 12,016 each type. Yes.
Do we also include the overflow circuit, which is 1 XOR?
Overflow circuit, yeah, we can add it. Like as far as spec says, it didn't say anything about the overflow, but we can definitely add one more XOR, which will increase the NAND amount by 4 more. But that's okay. Like either these or if you add the overflow circuit, I think that would be also okay answer. Like,
okay.
Yeah.
Okay. Thank you.
But yes, try to stick to the spec, right? Specification said it's another subtractor. It doesn't say anything about this thing, your overflow circuit. If such confusion arises during exam, just ask me.
Thank you.
Okay, now, so let's remember this number, this many MOS, okay? Now, let me give you some interesting insight with numbers, okay? So let's say, let's say each MOS has, let's say, it's a 28 nanometer technology. So let's say it has this 28 nanometer by 28 nanometer footprint. What does it mean? Footprint means on a piece of silicon, you are basically printing this device, MOS device, with one side 28 nanometer and other side 28 nanometer. With that footprint, what is my like area needed on the chip for these add sub circuit? It's a straightforward answer. It's a 28 nanometer multiplied by 20 nanometer multiplied by sorry, I didn't realize I didn't change the frame. So here, each MOS has a 28 by 28 nanometer footprint. So let's say we are putting it on the silicon. Each of them takes a 28 nanometer by 28 nanometer space. So area needed for this circuit is that area multiplied by 2,432. 2,432, that area, which if we multiply it using calculator, it comes down to be like, careful with the unit. So this multiplication unit become nanometer square. So it is like exactly 1906688 nanometer square. If we turn it to the micrometer square, it is approximately 1.9 micrometer square. Okay, so each of them contains this. And usually a chip, a processor is, let's say it's fabricated on 1 millimeter by 1 millimeter area. So this is your microprocessor, okay? Microproc area. So question is like, just to give you a relative perspective, okay? How many adder and adder subtractor we can compact within this area? Answer is very simple, right? This area is 1 millimeter square. If I divide it with the 1.9 micrometer square, it will come down to be about 500,000. So within a 1 millimeter square by 1 millimeter square, you can pack like 500,000 adder transistor, adder subtractor circuit. Now, let me give you one more perspective. So 28 nanometer, at least we consider is the older technology node. We are going about 5 nanometers, which means this dimension become now 5 nanometer by 5 nanometers. Question is how much we can pack now. So it's a similar thing, like let's compute. So it is 2432 MOS. Now it will take 5 nanometer multiplied by 5 nanometer, which is about like, which is not about, it is 25 nanometers square. Okay. So total area will become like, so nanometer square multiplied by 32. I forgot that step. So if you compute that correctly, it will become about like 0.0608 micrometer square. This means on the same die area, 1 millimeter by 1 millimeter square, you can actually now pack 1 millimeter square by 0.0608 micrometer square, which is about 16.4 million of these devices onto that small area of 1 millimeter by 1 millimeter die or piece of silicon. So that's the enormity of moving towards the latest technologies, from like shrinking the technologies so that we can pack more and more and more functionality, more cache memories and all this stuff into the same chip. And it's going better and better day by day. Question? Okay, 8:16. Let's take a 5-minute break now then. We'll be back about 8:20, 8:21-ish. Okay, so let's get back to our discussion. Before I go into this topic, like which I basically intended to show you a 4-bit adder subtractor, like on a simulation platform, the model C. Any question? Okay, so do that. Let me share my screen with you all. Okay, so I have implemented these 4-bit example of adder subtractor combined, right? I started with an half adder, 1-bit half adder with a 1 XOR and 1 AND there, and then use that half adder to build a full adder with an input A, B, and CI as an input carry in and SN carry out as an output. And then I combine that full adder into a 4-bit adder subtractor circuit with that mode as an A. If it is this guy is 1, then it is subtraction. If this guy is 0, then that's addition with an input A, B, overflow detection, and the result. And I exactly did what we studied on the slide for this adder subtractor. We have this 4 full bit adder, full adder, connected in a daisy chain fashion with an XOR on the B side to make that flip between subtractor and addition, that inversion computation based on the mode. And then I stuck in the first stage carrying as this mode, just described as in that slide. And also I added one XOR to overflow detection. Then I have this simple test bench where I instantiated that 4-bit adder subtractor, initiate all the values with zeros, and then in a loop, like this is 4-bit adder. So a 2's complement sign gives me that it is a range from -8 to 7, right? That is the value range it can represent. So that's why I'm looping between -8 to 7. To like one I is going for the A and B is assigned with the J. J is like for each value of I basically looping another 8 to 7 and trying both the addition and subtraction 5 nanosecond apart. So that's my test bench. With that, I have added this A, B, SNA and result. Let's SNA mode go up. And this is the circuit looks like. This is exactly then SNA is applied on the B with the XOR, and that is being fed to this individual full adder circuit. And this XOR instant 0 1 is my overflow circuit. So if I now simulate this one, let's see what we'll have. So you see, like I can see at least from the overflow side, many of these are overflowed. Some of them has correct result. And let's look at a couple of sample and convince ourselves that this is doing the right thing. So do that. Let me do one thing. Change. Okay, so go to the top. Change the radix of this guy to the decimal. This guy radix to the decimal. And result radix to the decimal. So you see at this point, for example, both my operand are -8, -8. Let me plot one more. The result bit is 0, but my overflow bit is 1, it is expected, right? -8 plus -8 is basically -16, which is out of range with the 4-bit 2's complement format, and our circuit correctly detected that. Whereas if I do a subtraction with the same data, -8 -8, that becomes like -8 plus 8, which results in 0, and of course that is not an overflow. We do repeat the same thing. Let's get a sample of, okay, this one, like -8 plus 0, which result to -8, that's correct, and no overflow. Whereas -8 plus -1, that's result in -9, which is an overflow. That's basically indicating that. So no matter what comes out of the result, if overflow bit is 1, then we should discard that result from the addition subtraction. If we go to the other end of this simulation, what we'll see is, let's pick up this one, right? Okay, maybe, yeah, this one, let's say, which is like 7 on the one side, other side is 4, and it's on subtraction, which is 7 minus 4 is 3, and no overflow. Whereas if it comes to this guy, which is like A is 7, D is 4, 7, 4, yeah, 7, 4, addition result is 11 plus 11, which is out of the range for the 4-bit. It is the addition operation. So we have an overflow right there. So seems like this overall, this circuit is working okay. We can do more automation on the test bench to like compare with the expected value and so on and so forth. But at least visually we can see that this is working okay. Question? Okay, now I will explain one thing that you guys ought to remind me about, that mystery about the stop. Like, see, this test bench doesn't have a stop, but it didn't cause a problem, right? But usually I like to give you this test bench with a stop, at least a definitive stop. Why so? The explanation is this. This test bench, if you see, it creates event, right? It creates event, and for its event, what is happening, what I mean by event, is exactly like at some point of time, some logic value is changing. Each logic value change is an event to the simulator. So as long as an event is generated, and for the simulator, it is like an event generate, means logic change generated, and it is shown into a queue, event queue. So as long as there is an event in the event queue, simulators keeps on running. So in this test bench, what is happening after this both outer loop and inner loop is done, there is no more event is being created. Like no other module is creating any event, any logic change whatsoever. So that's why this having a stop is not a mandatory. It's over, event queue is empty, simulator just stop there. But in the circuit, in the test bench and circuit like the other one, let me open up one sample for you. Maybe from the, oh yeah, test bench, this test bench. Now look at this one. This needs a stop, absolutely need a stop. Let me first explain why. Because it has two blocks, like this initial block has some loop for generating some pattern, right? Some bit changes, some event, it generates some event put in the queue. Also, it has an always block. Look at this code. This is always means like infinite time. For infinite times, every 5 nanoseconds, toggle the clock logic. So that means this event will be created indefinitely and pushed into the event queue, and model sim will try to crunch on that event and look at all the events and propagate the effect throughout the circuit. So that becomes a never ending simulation, right? So if we actually, like delete this stop, you'll see the simulation is not going to end. And after some times, I think this is a evaluation version for the student or student revision version. So it will basically tell you that, okay, you reached this many iteration limits. So I'm just bailing you out. But point is that since the event, at least one event, there can be more than one event, but at least one event is being created indefinitely, then simulation has to know where to stop. And that's where this stop is. So it's a definitive stop. I don't care about the clock event. As long as I'm testing with all the patterns, they're done, just wait for 10 more nanoseconds and stop my simulation. So that's where the stop is needed. And this guy doesn't need that. It is not no block, code block is generating indefinite events. For the indefinite times, it doesn't need a dollar stop. Is that clear for everybody? I hope I could explain that. I was more thinking like before it was like maybe a newer revision of the model sim doesn't need a stop and stuff like that. Then I kind of little bit thought myself what is actually going on with the simulator, and this should be the explanation. Question? All right, if we don't have any more question, we can stop right here tonight, and we'll all see you on this Wednesday with the multiplier and division circuits. Please read that, watch the videos. And by the way, don't forget to work on your project too. That's very important.